right, let's go through a review sheet. There are two right-hand rules we're using. One is when you have a charged particle moving in a magnetic field. Always put your fingers in the direction of the magnetic field. Your thumb is in the direction of the velocity of the particle, and your palm is always going to face the direction of the force. When you have an electron, switch your answer. No matter what your answer is, whether it's force, magnetic field, or velocity, just go through and do the computation or do the directional, and then flip your answer. So a lot of times you'll just hear me say flip it. Now, if you have a bunch of charges moving in a current, stick your thumb in the direction of the current, and then the magnetic field will be in concentric circles around the wire. And let's see these. Magnetism and electricity are the same. No, they're not. They're related, but they're not the same. Three metals that can be magnetized: iron, cobalt, nickel. What is the law of magnetic poles? Let's see. Opposites attract. North attracts south. And then north repels north. What causes magnetic fields? Moving electric charges. What causes magnetic fields to become permanent magnets? What causes the magnetic field in a permanent magnet? Okay, well, you kind of have to look at this. In a permanent magnet, you have the domains all lined up. So you have aligned domains. Now, there are always two poles in a magnet, north and south. You cannot have a monopole. There's no such thing. Now, the geographic north pole of the Earth is a south pole because you remember north attracts south. So in order for the north pole of your compass to point to our geographic north or even magnetic north, that means it's being attracted to a south pole. The angle difference between geographic north and magnetic north is a magnetic declination. Explain two ways to produce a temporary magnet. Well, you can take any metal and put it in a strong magnetic field, or stroke a non-magnet with a magnet. Where is the field of a magnet strongest? Of course, at the poles. What did the iron filings and compass needle line up with at the magnetism lab? Of course, it was, again, the poles. That's where the magnetic field is strongest. Sketch the domains in a piece of iron before and after it's magnetized. Now, before it's magnetized, the domains are all random. Okay? They're pointing in all kinds of directions. Some are going up, some are going down, some are going sideways, some are going in kind of these weird cattywampus sorts of ways. It doesn't matter which direction you draw them. Clearly, your domains don't have to be the same as mine. However, once they're lined up, they all go in the same direction. Now remember, a domain is merely an area where all of the magnetic fields are pointing in the same direction. This takes a lot longer to draw. Okay? So here's a magnetic field. This is not magnetized. Sketch a field lines around the following bar magnets. Remember, they start on north and end on south, and they make these nice little loops. How many loops do you put? Well, it depends. Let's see, this is probably enough for me today. What surrounds the Earth and protects us from harmful electromagnetic radiation? Magnetic fields. A magnetic field surrounds the Earth, a magnetic field surrounds a current carrying wire. So if you have a current carrying wire, you're going to have a magnetic field doing loops around. What do we call a current carrying wire wrapped in consecutive loops? A solenoid. Describe 3 ways an electromagnet can be made stronger. Well, you can increase the current, the loops, or you can actually put iron bars in the middle. That's kind of cool. You need to know 3 technologies, at least, for magnets or electromagnets. Of course, the Japanese electromagnetic trains are essential. Lifting cars, like in junkyards, they use a lot of electromagnets there. Okay, climbing robots, not essential, but that's one of my goals for this year, to have a robot that can climb using magnets. What's the right-hand rule? Okay, let's see. I'm going to painfully draw fingers. Do you see your fingers? Here are your fingers. All right, and here's your palm. You have kind of a weird looking palm. That's okay. If you put your fingers in the direction of the magnetic field, your thumb in the direction of the velocity, then the force experienced by a particle will be shown by the direction of your hand. In what direction would the original force be on a positive charge? It's positive, traveling west, so the velocity is west through the following field. Now, that the field is a bunch of x's tells me the field B is down. B is down. So put your fingers down. Velocity is pointing to the west. And remember, west is this side of your page. Now look at your palm. Your palm is facing this direction. This direction is south. All right? So the force is to the south. In what direction would a negative charge? Now, what this tells me is no matter what direction I find, I'm going to flip the answer. If the magnetic force is north, so F is north, and it's in the following field. Now, in this case, the field is coming up out of the page. So, put your fingers out of the page. Put the, this is hard. Fingers out of the page. Force is the palm. So the force is to the north of your page. And you're going to see, let me try this again. I nearly broke my hand doing this one. Excuse me. Force is to the north of the page. And the magnetic field is out of the page. So B is out of the page. Force is to the north of the page. Okay, so force is your palm. That's going north. And your, let's see if I can do this again. Force is north, so your palm is north. Your finger's coming out of the page. So your thumb is pointing west, if you notice that. Your thumb is going west, but it's a negative charge, so your thumb, so the velocity is east. Let me check that again. B is out of the page, F is to the north page. Yep, velocity is definitely going east. Guys, even teachers have to think about this and check themselves, so do not feel bad if you find this challenging. Magnetic field is represented by a variable B, all right, and is measured in Teslas. Charge is represented by Q and is measured in coulombs. Force is measured in newtons and is measured in N's. Oh goodness, got carried away with myself. Newtons is, represented with the variable F. Goodness gracious, don't you just love it when we make mistakes? The variable is F. Velocity is measured in meters per second, and we use a V. Current has a variable I, but we measure it in amps. The length of a current carrying conductor is L, and we measure that in meters. Two current carrying wires parallel in the same direction are attractive. Two current carrying wires parallel with the current in opposite direction are repulsive. If a charged particle is traveling parallel to the field, there is no magnetic field, no magnetic force acting on it, or zero. If a charge is traveling perpendicular to a magnetic field, however, it has a maximum magnetic force. Lost my pen here. Okay, if an electron of charge Q is 1.6 times 10 to the negative 19 coulombs, is traveling east at a velocity of 100 meters per second, is pushed down with a force of 12 newtons. Find the magnitude of the magnetic field. All right, let's find the magnitude first. F is QVB. So B is F divided by QV. So it's 12 newtons divided by 1.6 times 10 to the negative 19 times V is 100. So this is 12 divided by 1.6 times 10 to the negative 17, or 7.5 times 10 to the 17 Teslas. Let's find the direction. It's an electron, so no matter what we find, we're going to flip the answer. It's traveling east, so the velocity is east. It's pushed down, so the force is down. Now we want the magnetic field. So put your thumb east. All right. Let's see if we can do this. With the force going down. And what you're going to see is your fingers are going to point downward, but it's an electron. So it turns out B is north. Flip your answer because your fingers are pointing down and it's an electron. That means your fingers should point up or north. All right, a 5-meter long wire. L is 5 meters. 5 amp current. I is 5 amps. Runs west, so I is going west. Through a magnetic field, B of 2 Teslas. And B is pointing north. Oh goodness, pen doesn't want to work. What's the magnitude and direction of the force? Okay, F equals ILB. So it's 5 amps times 5 meters times 2 Teslas, or 50 newtons. Let's find the direction. It's either going to be up or down. Put your fingers up toward north. Your thumb points west. Did I do this right? The force on the wire is down. It is not up. Ooh, made a mistake. Happens. Now, I'm going to check it. It's kind of late. A 5-meter wire carrying 5 amps runs west. So my thumb is going west. Through a magnetic field of 2 Teslas, B is north, so my fingers are going north. And it turns out the force is definitely down. Oops, made a mistake. Down is the answer. Now my pen wants to act up. All right, a proton of charge Q equals 1.6 times 10 to the negative 19 coulombs is moving east. So V is east. Experiences a force of 5.5 times 10 to the negative 25th newtons upward. So F is up. At this location, the field has a magnitude. B is 8 times 10 to the negative 5th Teslas north. So B, let me check. B, well, if B is north, and, oh, goodness gracious, is moving east. Y'all didn't catch me. That's why I don't like doing this at home. It's going east. If B is to the north and V is east, then force is up. So I do have my directions right. Find the speed. F equals Q, V, B. So V is F divided by QB. F is 5.5 times 10 to the negative 25 divided by Q, which is 1.6 times 10 to the negative 19 coulombs, times B, which is 8 times 10 to the negative 5. Now I know this is a hassle, but go on and do it. 5.5 times 10 to the negative 25. Now multiply 1.6 times 10 to the negative 19 by 8 times 10 to the negative 5. And you get 1.2. 8 times 10 to the negative 23. Divide 5.5 times 10 to the negative 25 by 1.28 times 10 to the negative 23. And I just got a weird answer, so let me redo it. 5.5 times 10 to the negative 25 divided by 1.28 times 10 to the negative 23. Ah, now I get 0.04968, so let's call that 3 meters per second. Guys, I have to check my numbers, you check yours. A wire 12 meters long, so that's L, is 12 meters, carries a current of 5 amps, I equals 5 amps, and it's to the west. If it has a maximum magnetic force on the wire, points downward. So B points downward and has a magnitude of 5 times 10 to the negative 2 newtons. Goodness, I just said force and I wrote down B, didn't I? So I need force. So if the force is 5 times 10 to the negative 2 newtons, I don't like my N here, let me fix it. Find the magnitude and direction of the field. All right, put your thumb pointing to the west, your magnetic field pointing down, your magnetic field's pointing, oh, magnetic force is pointing downward. I just totally missed this one altogether, didn't I? I read one thing and I meant another. The force is going downward. So if I is going to the west and F is downward, I see that my magnetic field, B, is pointing up. And up, of course, is north, where the bottom of your page is south, east of your, right of your page is east, left of your page is west. So, F equals ILB. So, I'm looking for B, which is F, divided by IL. The force is 5 times 10 to the negative 2 newtons. I is 5 amps. L is 12. So this is 5 times 10 to the negative 2 divided by, let's see, 5 times 12 is 60. So you get a magnetic field of 8.3 times 10 to the negative 4 Teslas, and the direction is north. Now the magnetic force acting on a wire perpendicular to a 1.5 Tesla So B equals 1.5 Tesla. Magnetic field is 4.4 newtons. So F equals 4.4 newtons. If the current is 5 amps, I equals 5 amps. What's the length of the wire? F equals ILB. Now there's no direction in this one. So L is F divided by IB. F is 4.4 newtons. I is 5 amps. B is 1.5. So this is 4.4 divided by, now go on and multiply 5 times 1.5 and you get 7.5 in your denominator. 7.5. Now 4.4 divided by 7.5 gives you 0.5867 meters. Close enough. Finally, if the current in a wire 3 meters long, so L is 3 meters, running from north to south. Oh, north to south. Goodness gracious. Y'all would all get a gumball for that one. Perpendicular to a magnetic field, B is 1 Tesla, experiences a force, F, of 9 newtons. What's the magnitude of the current? F equals ILB. So I is F divided by LB. F is 9 newtons, L is 3 meters, B is 1. So this is 9 divided by 3, or 3, whoops, lost my pen, 3 amps.